let's investigate the effect of position on current strength in a series circuit. So we want to build this circuit. Notice that we have a battery. There's its positive terminal connected to an ammeter, which measures current strength. We have an open switch here. There's a resistor. We can see from the color coding of the bars that the value of this resistor, the resistance of this resistor, is 10 ohms. Then we have another ammeter, a bulb, another ammeter, another 10 ohm resistor connected by a wire, a good conductor, to another ammeter, and that's connected to the negative terminal of the battery. That's a picture of the circuit. Here we have a circuit diagram of the circuit. You can see there's the symbol for the battery or cell. There's an ammeter, switch, resistor, ammeter, bulb, ammeter, resistor, ammeter, and we can see there's the negative terminal, there's the positive terminal of the battery, of the cell. So now we need to build the circuit. We open our simulation, circuit construction kit DC. We open the lab. We put in a battery. There's one of the resistors. There's the bulb. There's the other resistor. So we have two resistors on either side of a bulb. Now we put our ammeters in. We have quite a number of ammeters because we want to see whether the ammeters at different positions give different readings. So we put our ammeters, our 4 ammeters in, connect everything together. There's the last ammeter. Now what we need to do is to close the gaps with wires. We put in the switch first of all so that we can open and close the circuit, and now we put in the wires. So now we're going to close the last gap, and there we have our completed circuit. Well, it's not complete because we need to close the switch still. So we haven't closed the switch yet because you first need to predict what you think you're going to see. Before you can do that, we need to write down the question that we're asking in this investigation. How does independent variable affect dependent variable? And then we can give a description of the context after that in a certain context. What needs to go on those lines? The independent variable is a thing that we make different between our treatments. Now in this case, we don't have different circuits as our different treatments, but each of our measurements is a treatment. So what is different between the ammeters shown here? And that is our independent variable. And what are we trying to see whether that affects? The thing that is different between the ammeters is their position. So ammeter position is our independent variable, and we want to see whether we will get a different current strength reading at those different ammeter positions. So our question is, how does ammeter position affect current strength in a series circuit? Or we could say, how does ammeter position affect the current strength that we measure in a series circuit? What needs to be the same so that this is fair? The ammeters are all in the same circuit, and it's a series circuit. And so all the aspects of the circuit are the same, which includes that we have the same battery, 9-volt battery, and the same resistance of the circuit. So what is your prediction? How are these ammeter readings going to differ? Is A1 going to be maybe the highest? Does the current go fastest just outside of the positive terminal at A1? Or maybe A4 is going to be the fastest? How are A2 and A3 going to compare? Are they going to be the same? Is one going to be greater? How will these ammeter readings compare? And why do you say this? So now we go back to our simulation, we close the switch, and what do we see? All the ammeters read the same reading. Is that what you predicted? Why do they all read the same reading? Before we can discuss that, we need a table into which we can put our data. Our question is, how does ammeter position affect current strength in a series circuit? And we need to write a heading for our table showing the relationship between the independent variable and the dependent variable in, give the context, and then we need 2 columns. We need a heading and maybe a unit. You have to decide whether that's relevant or not, for the independent variable in the first column, and then also for the second column for the dependent variable. So what comes in these gaps? I hope this is what you gave. Table showing the relationship between ammeter position and current strength in a series circuit. circuit. Ammeter position does not have a unit, but current strength does. Amperes, shortened as an A. So what ammeter positions did we have? Now we could describe them, or we could simply refer to our circuit diagram. We call the positions A1, A2, A3, A4. So we could put those same numbers into our table, and then using the circuit diagram, it's clear what we mean. Now we need to put the current strengths that we measured in our simulation into the table, and we found 0.3 amperes at every position within the circuit. So we put that into our table. So what is our conclusion? How do we answer this question? How does ammeter position affect current strength in a series circuit? And I hope what you said is ammeter position does not affect current strength in a series circuit. Or put another way, current strength is the same at all points in a series circuit. Now we need to explain why is that. And this marble analogy can help us to do that. The marbles represent electrons that are in the wires. And just like the marbles are all touching another marble, there are no spaces between the marbles. In the same way, the electrons are incompressible. They cannot be squashed closer to one another. They cannot be stretched apart from one another. So can you see that it isn't possible to make some marbles move faster than others within this marble circuit? When you push the marbles, they all have to move at the same rate. Because if some went faster than others, they'd have to overtake, they'd have to go on top of or squash others. And others would have to stretch or come apart. And that can't happen because they are incompressible. They can't be squashed or stretched. And so the rate at which the marbles moves is the same everywhere within a particular circuit, at all points within a circuit. And if we go back to the simulation and look at these electrons as they move, you can see that the electrons are moving at the same rate at all points within the circuit.